differentiability. So question 1 has f(x) equals x plus 2, and well, it's between 2 is 2 functions put together, really. Does anyone know what's called when you put these 2 functions together like this? Yep. Piecewise. Piecewise, yeah. So in other words, this function works up to 0, and I put it in the signs, which is I presume the bottom is wrong now. This one works up as far as 0, and then it kind of changes. So if you were to sketch this, I will use Desmos to actually sketch this in a second. It kind of, there's going to be a curve. It's going to go as far as 0, let's say, and then the line is going to take over. So tell me something like that.
That means it's not continuous, right?
I don't know yet.
How many differentials?
How do you know?
It's on the graph of the gradient function. It's not continuous. Yeah, exactly.
Yeah, it's not. Well, it's only at that point. Yeah.
I mean, it could be connected, but it's just it could be continuous. So that's the differential.
Okay. So, well, can we get So for all the black line here, could we get the rate of change?
Yes.
Yeah. All the black line here. Yeah, we can get the rate of change of that. The rate of change of this is going to be something constant. And it's going to be 1 anyway. The rate of change here of this is going to be a line. Now the question is, where one takes over from the other. That's the question. Well, that's what we have to do. Sometimes it is, sometimes it's not. And that's what we have to find out. Because often with piecewise functions, and real life functions, sometimes they don't work for particular values for crossover. So let's have a look at the sketch of this first of all. So since I've done this up, I'll type it in. Now I want yes, 3. Okay, so there's the 2 of them, just as full functions. Now one takes over from the other, and you can see there's a gap there. They're going to take, one's going to take over from the other. Line takes over here at 0, and which 0 is on which line according to this? It's on the it's x plus 2. So when the function is at 0, you use x plus 2. When it's at minus 0.00001, you use this. I think. No, I didn't switch it to Desmos.
Oh, okay.
So all right. So how do we show that it's differentiable or continuous is not? And how do we know if it's continuous then? Is it continuous at that point? How do we know it's continuous?
No, it's not. You try if it comes from positive to negative direction to x equals 0.
What should you get? If it's continuous, what should you get?
Same value.
Yeah, so it's going towards the same value and it just picks up perfectly. So a continuous function may look like that. At this point, both functions work and then it continues on. Now clearly this one, at this point, there's a gap.
So it's not continuous.
Well, I proved it graphically to show it algebraically as well. So how do I show? Well, if I sub in 2, I suppose. So, or 0, sorry. If I sub in 0, as x approaches 0 from the negative direction, let's say. Sorry, but maybe negative there is better. What does the bottom part of this function give?
0.
0. So x squared plus 3x, that'd be 0 squared plus 3 times 3. So that's, okay, so. And as x approaches from the positive direction, so as it goes backwards, so it's coming back down, what's it coming towards? 0 plus 2, which is 2. Therefore, it is not. It's not continuous. And let's discuss, is it or is it not differentiable? So it's not continuous. Yeah. So it's not continuous because there's a pure geometry. Why wouldn't it be differentiable? It's differentiable at every other point. And why wouldn't it be differentiable at that point?
It will be a clear difference in scope. So, 2 points.
Well, yeah, it doesn't logically make sense that it could be going towards the rate of change would kind of jump at a particular point. And there can be two different rates of change in the same place. It doesn't really make sense that like rate of change, fine, it takes over after here. But at zero, no, it won't work because it's not continuous. Okay, and you kind of probably read that in the text. If it's, that's where it says, I think, x equals a, if x doesn't equal a, it approaches from both directions, something like that, it won't be differentiable. Is it differentiable if it is continuous?
Yeah. That needs to connect, the second graph needs to connect to the first one.
Okay, well, let's look at the questions you had for homework, so I think that might help us with that. That was question 1. We would have stopped at 0, because 2 didn't equal 0, whatever you want. So let's look at question, well, let's do question 6. Let, so this is telling us something. So let x, so once again, piecewise function, and we have ax squared, and we have x plus b. This one takes over at 2, I think.
Yeah.
I hope I got that less than or equal to. Okay. A and B, find A and B such that f of x is differentiable. So, find A and B such that it is. Yeah, it's telling you it's continuous, and it's telling you it is differentiable. We've got to use those two bits of information. Well, we actually only say differentiable at x equals 2. Okay, so talk to me about what I need to do.
Well, you can do it if you're plugging to ax squared and x plus b and
okay, so we know that one takes over from the other same spot, so there's two outputs, the two y values, if you shove it in, must be the same. So a to the 2 squared must equal 2 plus b. Yeah? That's 4a is equal to 2 plus b. Okay.
one equation, you have a bit of
okay, so it's continuous. I've got that sorry, lost in there. Like, so that's using the fact that if it's differentiable at 2, it's continuous at 2. So now you're going to use differentiable at 2. That means you probably need to differentiate that 2. So what's the, Justin, what's the differentiation of this by rule? So multiply down to the power 2. Root. Oh, you made it too complicated. Just this. It's just 2ax, isn't it? Multiply down by 2. That's a variable. So if it was 3, I'd multiply 2 times 3, but I don't know what it is. So just multiply 2 times a. And then take 1 away from the power, so 2ax. But now what's the differentiation of this?
1 plus b.
What's b? We don't know what it is, but so it's a constant. Okay, so let's say it is 3. What's the differentiation of that?
4.
Derive that to 4? No.
Like, if it's a single variable, it would be 1, right?
Yes, correct. So that's correctly differentiated.
Oh, right, the constant equals 0, not that. So that's just going to be 1.
Thank you. All right. So we've got the derivatives, and now we know that it's also differentiable at 2. So what do they equal each other then at 2?
Yeah.
So 2a to the 2 now equals 1. So let them equal each other again because they're differentiable at that point. So that's going to give you 4a is equal to 1. A is then a quarter.
Yeah, you put in.
Yeah, that's 2, and if they know a is a quarter, that's 4 times a quarter, which is 1. Bring over the 2 minus 1.
So you equal to -1.
Yeah.
Do you find
Can you write a range?
like when you write the left half or when it tells you left half of x is greater than or equal to 2. And x is less than or equal to 2.
Yeah, one would take over. Yeah, so I could have written it here. Yeah.
What would it be?
Was it going to be the same thing?
It would be the same thing, right?
Is it going to be the same thing? That's asking.
Yes, it's a different.
Well, yeah, if we look back at our, remember we were looking at this x and y axis. Originally in your function, your x and y axis are just input output. In this second, when you get the derivative, the x and y axis is x and the function gradient. So that's fx. And that's x. So is there any reason to change the x domain?
No.
No, there's not. The x domain will stay the gradient.
The only time we do that is like it's a for example an absolute value function where the slopes change after one point.
Instantaneously at a point, slopes are the same thing. Yeah.
So is that different here?
Huh?
Is that also here?
The slopes are different at the same point. Yeah, they don't exist at that point. They don't know where it is, but
okay, yeah.
Because there's no.
If this was shifted over and they both met at the same point, or something like that, and it's a parabola that is type of line, or is it
Yeah.
line going on?
Yeah.
It would not be differentiable at that one point just because it's like a median change.
Well, what do you think? What do they have when they're actually parabola?
Yeah.
It wasn't differentiable. No. So
in that case, you would not say that the x is just greater than 2 and x plus.
yes, it would continue on with a gap, with a hole. So that if you were to draw it, it would be this thing with a hole in it. At that exact point, the hole would continue on.
So the absolute function is because we can't find the slope for when it has an instantaneous change, right?
Yeah, it's an instant change. Instantaneous change. It's a very small section, yeah, but it's good to discuss it. You have any question?
Like, when I think about it, this is a linear function, such a quadratic and x equals 2. Like, as a fixed tangent.
This one?
Yeah.
Does the linear function just touch?
X equals 2. That. Like, when a equals 1/4 and b equals bigger than 1.
Oh, did you draw it?
So,
What does it look like? So A is the number.
yeah, a is 1/4, b is negative 1.
That's what it is. So it's x squared over 2. And then we have b.
The x squared over 4. That's x squared, it's the x squared over 4. And it's x minus 1.
Yeah.
And they take over our point.
X equals 2.
Which is right there.
Yeah.
So at that instantaneous point,
The gradient of the gradient of x equals 2 is the same for both functions.
so the differentiation does make sense, although one is a line and one is a curve. You can see at that point,
it's
tangent changes,
that makes sense.
but they both have the same slope. Yeah, instantaneous.
Yeah. So the tangent is always like the gradient of a given point.
So this one is continuous because only because of that. If that,
It was any other slope, dude.
yeah, if that didn't make a tangent and actually cross, you turn that line slightly and cross here as well, then all of a sudden at that instantaneous point, it's continuous,
But it's
not differentiable. This one, because it hits at a tangent point, it's continuous and differentiable because you get the same slope when you put in 2. Because the actual curve is just at that slope at just that second. Yes.
Do you have like a different piecewise question, like one that doesn't say at x equals 2 find the gradient, right? And you equals you want to define the gradient for the entire function where it's like, equal to each other. This is something which is because the gradient at x equals 2 is the same, right?
Yeah, it only works to the same. Yeah. If they have told us it works, we also presume it doesn't. It's more likely that it doesn't work. This is the case part of that. All right, so let's talk about our rules of. All right, let's start with the change rule. Now you've already done this, but I want to talk about where it comes from and why it works and stuff like that. Okay, so where we start? Okay, so far we're okay by rule, hopefully. So we've got like x6 if our y is that. We know that the derivative changing y will change x, 6x to 5. And that's shouldn't be a major issue for anybody. Hopefully on that page we did that in first principles. We can go later if we want. We can bring that change right down to 0. But what happens when things get more complicated? As they do. Let's say we have x squared plus 1 power of 7. Now there's something, now maybe you've already done the chain rule in chapter 17, but presuming you have, you could expand that right out and use Pascal's triangle, because we know individually we can integrate individual terms or differentiate individual terms, no problem. This isn't an individual term anymore, but we could expand it into how many individual terms? 8? 8. Yeah, I think we get 8 individual terms. Yeah. Okay. What would be the power of that? The highest power. Yeah. 13. 13? 14? 14? 14? No, not differentiated. Yeah, okay, yeah. Just expanded, sorry. Yeah. And then differentiate or expecting 13. Yeah. Okay.
So it'll be 13x to the power, 14x to the power 13 for the rest of the system.
Okay. So we're going to use what we do know and try and apply individual term differentiation to this new problem without having to expand it. Okay. And that requires me to introduce a new letter variable. So I'm going to say, start off with this one. I'm going to say, this is a useful skill to be able to do at any stage in any of your algebra work. Introduce a new variable and call it part of this. And this happens a lot in calculus, and it happens definitely a lot in integration. And then you can come back to this at the end. You can just work with u, because of course u is a lot easier to work with because it's something we've already done. U to the power of 7 can be differentiated. dy du instead of dy dx. Don't write it. It's just u. It's just different letters, same thing. What's dy du?
7u6.
7u6, no problem. Okay, so I've done that. What about u itself? I can derive this as two separate terms.
So is that du over dx?
That would be du over dx, yeah. What's du over dx?
2x.
2x, not plus 1, just 2x. Just 2x. Now I have 2 bits of information that aren't the answer in their own because I've got du here. Now, fractions. What is dy over du times du over dx?
dy over dx.
Why?
So du is cancelled.
Yeah, if you're dividing by the change in u and you're multiplying by the change in u, you're not really doing anything with u. So the derivative can be formed by combining these two, multiplying these two together. Okay, so multiplying these two, so dy over du, let's just put dy dx down here, because it equals this now, we've just done that. Dy over du was this thing, 7u to the 6 times du dx. Well, multiplication sign, I don't like it, but I will do. times 2x. Now I don't want u anymore, do I? I know what u is in terms of x. This is the derivative of kind of a mishmash of these two together. But if I put u back in, it's the derivative of this. 7, and I know u is x squared plus 1. The power of 6 times 2x. And that's the derivative of this. Only using what we knew already, how to derive a term. And I can simplify that a little bit, you don't have to, but I don't want the multiplication signs. I'm just going to multiply the first thing by the last thing, just to tidy it up a little bit. So I'm going to say 14x times x squared plus 1 to the power of 6. Talk to me about that expanded out. Are we happy that that would be to the power of 13 since it's a term?
Yes.
Because this would be to the power of 12, wasn't it? Wasn't it 6? And then times it by x again, it's going to be the power of 13. So we're happy that the derivative is 1 down.
Yeah.
Okay, the chain rule is essentially that. Now, did anyone do chain rule work with it yet?
I did it last year.
You did it last year? And
Maybe I did come across the chapter.
possibly, it's in chapter 7. Let's do the chain rule. Now we can do this process quickly, but I want you to do one first before I tell you how to do it quicker. I want you to differentiate y is equal to 4 over 3x plus 2 to the power of 3. You guys do that one first.
Or we just do it.
No, we don't have. I'm presuming you know nothing. I'm presuming that you only have what I just given you. We only know how to differentiate the term. Does it help? You want that help? Okay. I would make that the power of -3.
Yeah.
Probably.
But the quotient rule also.
I don't want. We don't know what the quotient rule is. I have never heard. Do not use the quotient rule. Whatever that is.
I don't remember.
Okay. So that's the first step. I want to make it look like the other one. So the power of -3. Now follow the steps I did. What you do the same thing. I would use u as 3x plus 2, yeah. Which means y is 4u to the -3. Be very careful. Negative. When I'm multiplying down by -3, -3 times 4 is going to be -12, yeah? So I have -12 u to the negative, well, what is it, -2 or -4? 2? So if I have, remember, if I have x to the 3, what's the derivative of that? 3x, take away 1, 2. Slow it down. Multiply down by -3. Take away 1 from the power. -4. Okay, that's that one's done. Sorry, that's dy du. This is the u, the x, when I differentiate this, and 3. Easy. Put them back together and multiply. That will get me the derivative. Y dx plus. Multiply. I'm going to multiply by 3 first, because I'll give me negative 36. U I'm going to put back in as I go. U is just going to be 3x plus 2 and negative.
Move that underneath. Or does it matter?
Okay.
You just move the x plus 2. Or does it matter?
Yeah, you could put it back down to the power 4 if you wanted. But yeah, so it's negative 36 over 3x plus 2. But this is perfectly fine. Is there a quicker way of doing this? Looks like it, sure does. This doesn't change anything, does it? That's still there. That's my question. That's my answer. It's in it. Yeah. So minus 3 times 4 is minus 12.
And then you times it by the coefficient.
You times it by not the coefficient, because remember this in this case it was the derivative of what's inside.
Oh, okay.
So in this case it was multiplied by 2x. Remember my answer had 14x in it. So yeah, you could speed this process up, but it's coming from this process. So generally, when you get quicker and quicker chain rule, you can probably do one just by looking at it. If I have y is equal to x squared plus 3x to the power of 7, my derivative, perhaps we can get there straight away. What is it?
6 times.
No, 7 times.
I mean, yeah, 7 times
X squared plus 3x to the power of 6 times
x squared plus
X plus
2x plus 3. Yeah.
3x plus.
Yeah, you can put it back together whatever way you want. So this is a quick jump in chain rule that you must make sure you know it's coming from this. So how do we write that? This is, if you want, you can say that's the derivative of inside the brackets, parentheses, whatever you want to call them. And this is kind of the derivative of, okay, all of that. And all of this is the derivative of outside the bracket. And that's not entirely a very mathematical way of looking at it, but it is a quick way of getting there. So you imagine this is just like an x derive this. Don't worry about inside the bracket, and then afterwards you multiply it by deriving what's inside the bracket. That is the chain rule. Very important. Okay. Let's move along. Let's take a product rule. Now we're not going to derive the product rule. We will derive the quotient rule. Product rule is very hard to derive. It's very long. Theorem, I suppose, behind it. But okay. What we have so far in our locker is, let's write this correctly. The derivative of x, this is the way we kind of write it, and you don't define y, it's just the derivative of something. U to the x plus v to the x. So perhaps when you did this, you remember coming across u and v when there's products and sums and quotients involved. Maybe we did. How does that say? This is just what we've dealt with so far. This is a sum of derivatives. In other words, an example, let's use an example next. In other words, what's 3x squared plus 2x? Is it just it's derived? Is it just, sorry, let's use u dash x plus b dash x. Does that follow?
Yeah. I think so.
Yeah, it is. We know that. They're just it's okay to do individual terms and then add together. That works. Does the same thing work for the product? You can't have a fail in one, otherwise I wouldn't be doing it. Product. So is the derivative of d, so two things multiplied together, multiplied by vx, does it equal, just I'll put it below it, does it equal u dash x times v dash x? Let's have a little look at the example.
What was the x then? X open parentheses.
No, you're just telling me the formula.
Yeah.
Remember, we don't know anything.
Yeah. Okay.
Okay, so we gotta think about this. Let's think about a very simple multiplication. 5 times x. 5 times x. Okay, so that's, if you were to graph it, it would be a line limit. It has a constant rate of change. So its derivative would just be at 5. So it's 5, it's always going up over 1, up 5, over 1, up 5. Constant rate of change. Okay, let's test. So we know that, so that's our function. Let's call it, so that's u and v, yeah? Does u dash multiplied by v dash give us what we know to be true? U dash, that's a u, is the derivative of 5, a constant, is
0.
0. Our rate can pretty much stop that. Times 1
So it doesn't give the
does not equal the 5 that we know the answer to be. The slope of that line is 5 constantly. That's y is equal to 5x. That's, we know this rate of change that, and it's definitely not 1. It goes over 1 up 5, over 1 up 5. So that means this
does not work.
not work. No, doesn't work. So we need an alternative rule for that. This one I'm going to give you without proving. There is a proof for it, but it requires a lot of, it would take up 2 boards worth of first principles work. It's usually, it does prove using first principles. Perhaps if we get time at the end of the unit, I'll go back and prove it. But it is v u dash plus u v dash. That is the derivative of a product. So if y is equal to u times v, the derivative is the second one times the first derivative, plus the first one times the second derivative. Now, the only thing we have, if I'm not going to prove it at my disposal, is a simple example. Y is 5x. Let's make it work for our simple example. The derivative then of the second term, derivative of the second term here, or sorry, no, just the second term, v is, that's going to be v, and that's going to be u. My v's and u's look a bit similar. Sure. Oh, you turn off the air conditioning there. That's over there. Okay. So let's do some examples. V is going to be x, isn't it, Justin? What's u dash? Yeah. So u is 5. 0. Plus u is 5 times v dash. So what's the derivative of x, Justin? 1. 0 times x is 0. 5 times 1 is 5. The derivative is 5. Now this is an example that we knew already. We knew the derivative of 5x is 5, but it also works with the product rule. So let's make it work in a more difficult example. So the product rule works. Here it is. It's the second term by the derivative of the first term plus the first term by the derivative of the second term. Now you'll never have to do 5x with it. 5x you know by rule. So we'll pick one. Perhaps. Do I have an example? Yeah, let's pick a tricky one. So I want the derivative of jump straight into a difficult one. If you do it first. There's a chain rule inside a product rule here. Jump straight into it, very good. So I must first define U and V. U, let's use different color, is going to be x squared plus 1 to the 7. And V is going to be 5x squared minus x. So I have defined them separately because I know that this is U times V. There's the times here if you want. Okay. Now that means I also need U dash and V dash. U dash is the first derivative, the derivative of U. And V dash is the derivative of V. And the derivative of V is not too bad, but the derivative of U is the tricky. Nah, not really. Just tidy it up as much as you can. Just maybe put power 6 last. That makes sense.
Be expanded or?
No, don't expand it. No, that would take a long time. Okay, let's just get to the point here. Justin, can you give me the derivative of this? And x minus 1. Could I, this one?
7 times x squared plus 1 to the power 6.
Yep. And?
Times x squared plus 1.
No, times 2x. The derivative.
Yeah.
Yeah, the chain rules. I mean, they did the chain rule within the product rule question. Yeah, so that's the chain rule, yeah. So derive the outside and then multiply it by derive the inside. Okay, now what's my derivative? So dy dx will be, this is in your formula booklet. V 5x squared minus x, so that's V. U dash then is this horrible looking thing. Times, well, that's 14x. Let's give that a 14x, 2x and 7x, and times x squared plus 1. No, plus 1. 6. That's V plus U dash. Now I'm going to do U, which is this thing. X squared plus 1. 7. Times V dash, which is 10x. Now, you could factor out maybe an x squared plus 1 to the power 6, perhaps. and tighten it up a little bit, multiply in the 14x. But we won't bother. This is what happens when you make up a question in your head. It doesn't simplify anything, but that's okay. It won't happen all the time. Does that make sense? Does you okay with that?
Yeah, that's right.
Okay, so we are just replacing this one. All right, so let's look at and recap what we got so far. So we have sum change product. So sum, we know that that is when we have ux plus vx to be differentiated. So if that's fx, let's say, the derivative of it, f dash x. So I'm switching between fx, f dash x, and y and dy dx because they're constantly interchangeable as well. And even this notation, that's just the derivative of, without quite referring to y, because y isn't in the question. So if it's just adding, we're okay to separate them. And that's just getting the derivative here, from here to here. We're okay with dealing with different terms. If we have a chain rule, we're okay with that. I suppose we could write that u times b to the x. If you want to write it like that. It's probably better off if you got an example for this, but it is, how about I write that then? U times b to the x. It'd be, how do I write it with u's and dashes and b times? Okay. Let me start it off with b dash x at the end. So now I end up doing this. This is Vx here like that, because that kind of stayed the same.
Do we have a power, like, to the power?
Yeah, no, you're on the right track.
Something minus 1.
It's u1x. This is the way they would write it, but it's far better off to remember the rule. And in the formula booklet, they use, I'll remove that. They use the y. I use them things, this isn't great. The u dx multiplied by dy du. That's the one that you would see in formula. Okay, but we know how to deal with a chain rule question, so I'll just write it again. Vx in the brackets like that. And u, just u outside, isn't it? I want to make sure I don't make a mistake there. I don't like this terminology, but I want you to just continue it. Product rule then is the one we just dealt with, which we didn't prove. It is provable. You can more than look up that. But in this terminology, u to the x times v to the x is equal to, well, this is, let's just do v u dash plus u v dash. So we got those things. I can put in ux, dx, and all that, but we won't. And now we come to the quotient. The bracket.
Quotient actually like useful, or is it just something that is a little easier than to use in machine?
No, not every quotient will work on machine. You'll see that in a second. So the quotient in general would be ux over vx. And what does that mean? What we're going to do is use what we know, the sum chain product, to find what the quotient is. We're going to find those of you who worked ahead in the textbook, perhaps you know it already, or those of you who did it last year, perhaps you know it already. But it's interesting to know where it comes from. Let's talk about quotient first of all. Here's an example, 3 times 2. That's quotient. Actually, how do I write that as product? 2 things. 3 times 2. Yeah, that's a quotient. I'm going to write it as a product. You can have a quotient in the products. Yeah. Okay. Well, yeah, you're jumping straight to it. Yeah, you can do 3 times 1/5, which is 3 times 5 to the negative 1. So therefore, I have enough weapons to be able to solve the quotient using the product rule. We don't need the quotient rule either, because we can rewrite the quotient in product form. Let's say the theory behind it. So that means this to be rewritten as a, how do I write it? If I want to write it like that, u to the x times dx to the negative. Yes. And now I have a way of doing this, because we just did it. Right, there it is. Well, let's do it. What's the next line then? This is just purely theoretical. We do not have two different, we're not dividing one by the other. What is v in this case? Well, we're just doing this. So we're now using the product rule. That's u, that's v. Yeah, we're going to do the product rule. And we're just going to apply this rule. We did. So v is the second thing. V to the x minus 1. U dash is just u dash. Yeah. I can't really do much more, but they're multiplied. U dash x. Okay, it is what it is. I don't know what it is. Plus u, which is ux, times, now, I need to get the derivative of this. This is what rule? When we have a power like this. Chain. Yeah, remember we had to the power of 7, to the power of 6. So how do we do this? What is it? It's going to be multiplied down by the power.
Minus 1 minus 1.
Yeah, so it's still going to be v to the x.
Yeah.
Minus 1 minus 1, which is minus 2. That's going to be times by something.
Times
the dash x.
Yeah.
The derivative of what's inside here. Okay. Still not looking amazing. Let's rewrite this. I'm going to use this negative one and I'm going to put it back down. U dash x all over v to the x. Plus, no, hold on, not minus. It's going to be minus now, isn't it? Let's just make that all minus. Minus u to the x, that one, this one, is what I'm going to do, times v dash to the x. I'm going to divide, I'm going to put that back down. Put it positive. V to the x squared. Okay, what do you do when you have two fractions? You want to add them or subtract them? Common denominator. What's my common denominator? No, it has to be vx squared, because that's vx squared. That's a vx, so I got to multiply this by vx over vx.
Yep.
Okay, and so it's going to be all over vx. V squared. That's probably in brackets like that, yeah. Vx v squared. Should have been those brackets. Just so it's not doesn't look like vx squared. It's all vx all squared. And that's going to be times vx times u dash x minus ux times v dash x. So just multiply that by that, and that's vx squared. Now, if I wrote that without the x, because it's all with x, I just wrote vx just v. This is what you see in most formal documents. Vx, let's call it v, times u dash x, which is u dash, minus u times v dash x, all over v squared. That is, that is the quotient rule. One that will work in every case. Derived from, not derived, well it is derived from a product. we use the product rule to form a general expression for something that was divided.
So that's the quotient rule?
That's the quotient rule. If it's u over v, so that's u over v. Similar to the product rule, but this is derived from the product of the chain combined. So the quotient rule, u over v, is b u dash minus u v dash all over v squared. So whatever the bottom one is times the derivative of the top, take away the top one by the derivative of the bottom, all over the bottom squared. And we proved derived it there. Let's look at an example using numbers now. Still cold? All right, just I don't have one, so let's. Right, so give me any term connection.
What do you mean?
An algebraic term, like a linear or quadratic or something.
Squared plus.
All right, Justin, give me another. Thank you. 2x minus. Okay, so we want to derive this. Now, first question: can I use the chain rule?
Yes.
Now, what you could think about is creating individual terms, if you want. I could do 3x squared over 2x minus 4 plus 5x over 2x minus 4 minus 2 over 2x minus 4.
Yeah.
All right, so to do that, don't do that. Don't take that down.
That's the way I did it.
You finished it?
No, like that's the way I would do it.
Okay, and what's your next step?
My next step would be to.
What's the derivative of this?
I would do 3x squared times 2x to the power. 2x minus 4 to the power negative 1.
Okay.
And the quotient rule for each one.
3x squared
Times 2x.
times 2x minus 4 to the minus 1.
Yeah.
Okay. So you can do product rule, product rule, product rule. Or you can do quotient rule, quotient rule, quotient rule. Or you could have just started with the quotient rule. Yeah. So yes, you could go down and split it all up individually, but you couldn't have used the chain rule, really. Well, could you? You could, I suppose, couldn't you? 2x minus 1, 2x minus 4 to the minus 1. Yeah, you could. I'm trying to give an example where you couldn't.
But based on that function, is u the numerator or denominator?
It's u over v.
Oh, u over v.
Yeah.
So u is the numerator.
Yes. So let's use, because one is derived from the other, you could have just done this. We started to do individual terms, which is right back to the sum, created 3 sums, but then using product rule. But it should be quicker just using u's and v's. So use the rule. V, which is just that, or which is the bottom, 2x minus 4. This is u over v. So this is v times the derivative of the top. So this is what you'll get into a habit of doing. You won't write u and v separately and get the derivative separately because you can do them as you go. Times that by that, so that's going to be 6x plus 5. That's u dash minus
3x squared plus 5x.
Yeah, 3x squared plus 5x minus 2. Okay, everyone knows space, but you hopefully haven't.
That's 2. And
That's u times just 2. So I'm just going to put that 2 in front of mine. Just because it fits. And that's v dash.
then v squared would be 4x squared.
Well, you don't need to do it. Generally, this is as far as you would go.
So you don't need to expand it.
Why would you?
Oh, so you can cancel it out. Like from the.
You can cancel out from here, can you? You could, but then you'd be back separating them. This still has to be divided by, all of this has to be divided by that. You can separate them again and divide that into that. You gotta look at what the question is gonna ask you next, as to whether you need to simplify that or just leave it as is. That's fine. It's messy, but it's fine. All right.
So wait, that's you literally just plugging values to the quotient rule, and that's it?
Yeah, but as you notice, you derive as you went.
Yeah.
Yeah.
Oh, so this is like,
Is this the farthest route?
I know, this is the farthest one, when they actually ask us to, yeah, like simplify.
Oh, see what? No, they're going to ask you. This is not dy, sorry, that's dy again.
The dy.
They're going to ask you then. This is the easy part. They're going to ask you to apply everything you know. These rules are just rules that, if you're doing SL maths, perhaps they'll give you some marks for doing that. Doing HL maths, they're just going to give you a question. They're going to talk about the gradient, perhaps rate change. They're going to say, well, what happens here and here? Is it continuous or whatever? Then you're going to have to use this to solve the problem. So let's look. I'll just pick a random one from the book. So this is chapter 17. I'll pick a quotient rule. Random problem. They're pretty straightforward at the start because you don't have still all the. All right. All right. So let's look. Question 6 on page 448. You don't need that, but if you're rewatching the video, you might. Question 6, page 448. So I haven't done this one yet, but it looks a little bit interesting. It gives us a function with a square root in it, which is always good. 2 root x is equal to 1 minus, or not equal to, divided by 1 minus x. They want you to find the derivative, and then for what values is the derivative 0 and undefined? So we'll get to that. So first of all, find. Okay. They actually want you to show that. It gives you the derivative. So see, can you get the derivative there? They want you to show that it equals x plus 1 all over the square root of x times 1 minus x squared. You got to make the derivative look like that. Try it.
We can use the quotient to use
That's what you want. We'll not tell you what to use. Thus the mod be the derivative here, 2x to the half is the derivative. So half multiplied down cancels out 2 to 1, yeah, and then subtract 1, 3 over 2, negative 1. I would perhaps you could write that as 1 over the square root of x then. When you're perhaps. What's the derivative of v, Vijay?
Of v?
Yeah.
Negative 1.
Yeah.
There.
Yeah.
I'm almost there, but I'm not asked for help.
Yeah.
I'm almost there to make that. I don't know how this makes sense to x. Because this will give me 2x.
And what are you doing with the minus 1?
Right?
What are you doing with this minus 1?
Oh, sorry, yes. This will be, so this will give me 2x. The power of 2. With 2x to the power of it won't equal 1x. So but this is the problem.
Well, if it doesn't, then yes, you have it, yeah. You write it. Or I do it. All right, so, Nigel, did you get it? So it's b first. So that'd be, I'm doing the derivative now, I'm putting these together. D is 1 minus x times the derivative of u, which was the derivative of u, now you give me the derivative of v. I'm going to stick with x to the minus a half for now. And that's minus the derivative, or u, sorry, so that's 2 to the x to the half times minus 1. The derivative. A all over 1 minus x squared. Well, that's okay, I got 1 minus x squared, that's lovely. Well, I'll just multiply this out and see what happens. X to the minus a half times 1, this is x to the minus a half.
X to 1.
Yeah, x times x, that's x to the 1, isn't it? Add the powers, x to the 1 half, so that's minus x to the 1 half.
Plus 2x to 1 half.
Plus 2x to the 1 half.
So then you're just left with x to the minus 1 half. Wait, is there still over that? Over that. Because one of them, they two of them to the cancel. So this is
One of them is 2 of them?
minus x.
Oh, so you've got to go 1 x to the half? 30%?
Yeah.
You sure?
Yeah.
Okay.
I'm not sure.
Yes.
I mean,
That was just equal to x negative 1, so it's going to be x times 1 minus
yeah, so that doesn't make sense.
Yeah, well, so you're saying you're sure that it's x to the negative a half minus, no, plus x to the half, is it? Plus 1 x to the half. Because 2 of them take away 1 of them. Just making sure.
Yeah, that's what I'm thinking, but after that, I don't know where to go.
I thought it's still minus.
Now, there's 2 of them here. and I take away 1.
Oh, okay, right.
All right. Now I want to make it look like that. How do I do that? Well,
Use a different rule.
Oh, you should
factorize. Factorize. That's 1 over root x plus root x. Yeah? All over. The bottom will come to in a second. Now I want x plus 1 here.
Right, so we're gonna have to divide it by root x as well.
Well, how do I get
You want to multiply by root x and x, right?
multiply by root x and root x? Okay.
So make it common denominator.
Well, I multiply this by root x and root x to get a common denominator.
Right,
What
so
happens here on top?
We get x.
X.
1 plus x over.
All right. So that's 1 plus root x plus x over root x. All over 1 minus x.
Oh, okay.
Now factor out 1. You can factor out 1 over root x can factor out. You get 1 left plus x. And 1 minus x squared. Now we have to be very confident that it's okay then to put the root x down here. Are we very confident?
Yeah.
Why? Because that's the solution. Yes. But also, because we know fractions really well, only from yourself. Continue. I think it's okay.
Yeah, but it's like,
Okay, 1/3 of 2 all over 5. That kind of what we got?
Oh, right, it's gonna be 2.
yeah, it's also like that 1 over x,
Yes, it's
or root x to the -1, right? So that can go underneath -1.
Because 1/3 of this will be 0 point something. We're not gonna be like 1 point.
You said you were confident, but you're only confident because it looks like the answer. But yes, 1/3 of 2 is 2/3.
Yeah, over 5. And then
2/3 split into 5. In other words, divided by 5 is 2 over 15, which is the same as 2 over 3 times 5, which was what we have here. So we can be confident in multiplying that by that. Can be confident just from our knowledge of supreme knowledge of fractions. What we have. All right. That's only part 1. Part B then, which I have here. Then, for what values of x is the derivative 0 and undefined?
this is like an asymptotic function.
With a fraction like that, yeah, it looks like it's going to have a rational function like that.
Yeah, right.
So it should probably have some asymptotes, yeah. All right, so you answer part B. Can I get rid of this? Anyone taking it down? Get rid of the top bit. All right, you guys answer part B then. For what values of x do you have this? They gave it to you in the question, so you could be able to answer it straight away without actually doing all that.
If you learn with the x, it's just gradient, right? So what value of x will the gradient be 0?
Well, like 0, x is negative.
Very good.
Sorry, what was that?
String it away, guys. So we have our derivative function, the function of the gradients put together, and it's saying what value of x will pop out a 0? What value of x will pop out a 0? So, in other words, if it gives out a 0 as the gradient, the gradient is 0. So since solving, multiply both sides by root x 1 minus x. Well, the gradient just cancels out, doesn't it? So we get 0 equals to x plus 1.
Oh, yeah.
When you multiply that by 0.
Let's say, isn't that how you let y intercepts? When you let y equal 0?
You could, yeah, that would be one way of finding y intercepts there. So that is a y intercept.
And x is 0, x equals 1.
X equals 0, x equals 1? Right.
Well, when x equals 0, it's defined by 0, the square root of 0 times whatever that is, doesn't matter, it's times 0, 0,
Okay.
5 by 0, undefined. If it's 1, 1 minus 1 is 0, 0 squared is 0, 0 times whatever that is.
Either is zero.
So you're gonna look, what you looked at, undefined, once I see undefined, what you're seeing undefined, is,
When it's divisible by divided by zero.
okay, so we look, yeah, if we see something divided by zero, we're happy with it.
Yeah.
So for undefined.
Oh, yeah, so it should be like x equals,
So what Rigel has done is root x over 1 minus x squared equals 0. It equals 0, isn't it? And 1 to be 0. And you said that you can take those set, what root x equals 0? And,
x, no, it's x.
okay, so x is 0. This is all definitely all 0, yes.
And when x is, oh, yeah, exactly.
When x is 1, that's 1 minus 1.
Yeah, so x equals 0, x equals 1.
Okay. Well, how was the next minus 1?
It'll be minus 2 squared, which will be 4.
When x is minus 1, it's 0. It's 0 divided by something.
Okay, well, how was the next one? Minus 2.
It'll be negative 3 squared, which will be 9 times.
Oh, yeah, so when x is 2,
Yeah.
1 minus 2.
That's right, I think it's minus 1.
Oh, sorry, negative 2. Yeah, so 1. Okay, so that'll be 9 times what?
Times 3. Oh, sorry, no.
X is negative 2.
2.
Yeah, so it'll be x times.
Oh, sorry.
X is negative 2.
Yeah, 9 times 2i? 2i.
9 times 2i.
Yeah.
Okay.
So 18.
The slope is
Imaginary.
up.
Is that also?
Is that okay?
If it's imaginary?
That's okay?
No, but if it doesn't say it has to be now.
If it's imaginary, does that mean it's also undefined?
What do you tell me?
I think so. Is it?
Well, yeah, it is undefined.
Yeah. So we have to set a domain, because any negative number works for the square root.
Any negative, so we can't have a negative square.
Yeah.
So x can be less than 0.
No, I can't.
It can be less than 0. X can be less than 0.
So if it's imaginary, it's just.
I want to see this drawn. Does anyone else interested to see it drawn and see what we're talking about here? Anything.
No, x has to be able to be graphed.
Well, let's look at the original function.
Negative
2 square root x all divided by.
Right, okay, so we can't do less than 2. Okay. And there's a vertical asymptotic 1 because is that just a no? Wait.
Yeah, on the original function, yeah. We can't get out y values that are real. On the original function, when x is below 0, it doesn't square root x. Okay. We also notice there will be an asymptote in the original, the same as the gradient. See that at 1. Because 1 is another mapping point. So we'll tend towards the not get. But then it should follow then that when we graph the gradient function, we'll also see those things on the same graph. Hopefully you will. X plus 1 is on top. Yeah. Divided by root x.
That's times 1 minus x squared. That's in the, yeah.
It's, this is just.
Gone. What the gradient function.
Yeah.
That's cool.
Well, because it's squared, so it's going to be like an absolute value almost.
So here's my original. Does the gradient function match the original function?
To some extent,
To some extent.
yeah. Like, it may not have the same y values, but it has the same shape.
Okay, let's talk about the slope just here, around here. The slope of the original function. Is it positive or negative at that point? Times at that point.
It's positive.
It's positive.
Yeah, that's just
Because it's negative. or is that section of the graph is negative? It's just almost like a reflection.
No, it's just the tangent of that would be positive, right? The tangent of that.
Oh, yeah.
Why is it? Is there a reason for reflection?
Because, I mean, you can't check it.
Because it's because
On that thing, on the lower right quadrant, all of the slopes are going to be positive.
yeah, because it's x squared. 1 minus x squared, so.
Yeah, well, yeah, it's equal 1 minus x squared, and it's going to take over, it's going to tend towards
0.
0, because it has the negative x.
Yeah.
The negative x would bring it down 0.
Okay,
So
so
the
that,
negative x line would bring that whole line. We can't get it because it's a root x. We can't get a root x. No. So, because minus would be a plus, and plus square would negative square. But it is interesting that, and we should see that relationship that, yes, it's a positive slope, but it's decreasing. The slope is decreasing, it's flattening out.
Yeah.
Instead, it's here.
it's squared.
It is a positive slope, but it's also decreasing and towards the slope called flat. Zero. And you can see here is a very sharp. This slope down here going down to the infinity is quite sharp. And a rule of a small bit over infinity. A rise of infinity over a small bit is very large number. See, that's what it's I'm saying that's going to tend towards it. And that's also tending. So it doesn't matter. So what's the answer? To the for what value of x is the derivative undefined? It'll be undefined from
Negative infinity to
0. Are you including 0? 0, okay?
yes. Yep. Yeah, negative infinity to 0, comma 1.
But I thought if we put in 0, we got x plus 1 over 0, which is undefined. So it can't be 0.
Yeah, exactly. So negative infinity to 0, comma 1, right?
It's just something greater than 0.
No, like when the function is defined, it'll be less than 0, comma 1.
So x is going to be
Okay, ended up from
x. Yeah. X. Wait, if you want to say what it could be, x is greater than 0, but not 1.
Yeah.
Yeah.
That's what it could be. So the opposite would be the case.
That's when it's that's when it is defined.
Yes. For what value is it undefined? When x is less than 0, less than or equal to 0, and
equals 1.
when x equals 1. Okay? Yeah. All right. Let's have a little look at exponentials before actually go further. So there's going to be many questions before on these. That's an example of how hard it can be asked at the moment, just based on here's the formulas now that we kind of to apply it. That's all about applying it because it's the gradient. Let's have a little look. Let's remove this here. At the okay. All right. The next exponential function. So this is decimal loss, I'm sure you've seen decimal loss. On decimal loss, you can actually get the derivatives. So if we have this function by that function, and I define it as fx, if I go down to my little calculator down here, most functions, you go to estimators, deal with the derivative, you can get a derivative, anything graph. So I didn't need to actually type all this in. What I could have done was just find that x equals, and then done this one, and then so I've already defined, one fx, otherwise it's confused with so just take one from the same time. So let's do that. Okay. So I'm looking at here extensions. Okay. So what I'm saying is about so you see how the way A works as A gets larger and larger and larger, it gets steeper and steeper and steeper. Hopefully you're seeing that. How about the derivative of that? So the derivative of that, you know, is also exponential in its slope. I know let's perhaps make it zoom in a little bit more. But you can see that the derivative looks exponential as well. So if A is 7.4, the derivative is actually, the gradients are actually increasing pretty much the same rate. Yeah. Slightly up.
But why is it, it's like it's translated?
It does, it looks a bit like it's translated, isn't it?
Is it?
It's not translated.
Yeah, it's not.
Okay. Well, notice what's happening. Watch the gradient.
It looks like they were.
So like if x equals maybe 3.
Is x around 3, isn't it? Let's switch it over.
No, 2.5.
So 2 point, okay, let's change my slide. Let's change my slide. Okay. So you're saying it's between 2 and 3, so 2
Yeah.
4. All right.
Yeah.
Let's
2.7.
let's watch this other question.
And oh yeah, that's 2.6.
Around 2.8.
Yeah, this is
All right, let's do 2.7 and
2.8.
2.8. I'm like, zoom in a little bit there.
That's slightly off.
Okay, slightly to the left now.
Which means it's too big.
Let's start at the start. It doesn't go through it at that point. Let's narrow that down. We do something. Watch the animation and tell me where to go from to next.
Yeah, the A value is too big.
2.8 is too big.
Yeah. I think it's got 2.7. 2.72.
Okay, that's 2.74 and 2.8 is too big. 2.7. 8.8. No, that crosses
Too
too
big,
big.
yeah. It's 2.72.
2.8, I think it's good. I think it's 2.79 and 2.76. I think it's around there.
2.7. No, but everyone is too big. Yes, that's very good. It should be 2.72 and 2.8, right? Everyone is too big.
2.72, you're saying?
Yeah, 2.71.
2.71? Yeah. And 2.73, you're there?
Yeah, let's talk about that.
Yeah, right there.
I think it's even more.
Oh, yeah.
So how about we just try to 2.7?
Actually, it looks like it's 2.7.
You want to try 2.718?
1.8
What's
to
a very
8.
specific value?
1.8 to 8.
1.8, oh, you got it further. That is 2.7. You want to see 2.718
7, 1.8 to 8, 1.8 to 8.
2
8, 1.8 to 8.
1.8. That's a very specific value. Let's get rid of slider. We just want to look at it. Okay, that's how we get rid of the off. Okay.
I can get it.
They don't like me.
I get it.
There
Well,
is one function in the world that is its own derivative. Can you look at all of the derivatives we have here? They're all very different variables. The right integrated math. Now, when we started looking at exponentials, and I started learning 10, you can see that the derivatives are similar to the original ones. So they shoot off, which means the rate of change also when we shoot it on. But there is one that is exactly the same. And it's at 2.718, 128, or whatever it is, 2818281. It's a very specific number. What is that number right? E. That is E.
oh, right.
E to the x is its own derivative of E to the x. And E to the x, where does another place E comes up? Yeah, it's in the natural laws, okay, but it's compound interest. Did you know compound interest? You know compound interest.
Yeah, we did it.
Yeah, it was in there, but we didn't really talk about it very much. Compound interest formula is 1 plus 1 over n times to the power of n. So n is the number of times it compounds in here. Right? So if you tend this function towards infinity, it tends, this function towards infinity, as n approaches infinity, the limit n approaches infinity, it goes to e. As this tends. So it doesn't you expect it to compound, of course. If you talk about compound interest, you think about, okay, so 1% after 1 year is 101, so you always expect it to go to 2, and even the second year, it looks like it's going to compound really infinitely. Yeah, it stops. It stops. Because you're getting a percentage of a percentage, and as soon as that percentage gets small, the percentage change gets so small, it tends towards the exact value, and that is e. And e in itself, of course, as we just said, y is e to the x. Its derivative is e to the x, and it's the only one. The only one. Everything else, it looks messy when you derive it. And exponentials are close. So a normal exponential, you see this in the book. Normal exponentials are close, but e to the x is perfectly a derivative of itself. So its slope at any point is so it is increasing as its rate.
That's what that is equal to f dash.
And that's where we need to say. So, does it work from the book, but it's just on those formulas? I'll give you a little bit on exponentials. For example, just want to, e to the x is okay, but e to the 2x, it's okay, it derives very easily, because if you do chain rule, e to the x stays in it, and you just end up deriving by the top bit. So that's just 2 e to the 2x. And you'll see that example for that in the book. You're just deriving this at the top.
Right.
Oh, yeah, because that's the same.
Yeah. So you can look at those new. I'll give you some of those. All right. I've recorded that, so you can watch it again. All right. So check out the homework. It'll be due on